Hello friends, welcome to this lecture, and in this lecture we will continue our study of compatible system. And if you recall, in a previous lecture we have discussed the definition of compatibility as follows. Here we say that f of x, y, z p q equal to 0 and g x, y, z p q equal to 0 are said to be compatible if every solution of first equation is a solution of second solution and vice versa. And then we have considered a method of finding at least one solution in common, that is let us assume that Jacobian of f g with respect to p q is non-zero and the corresponding dz equal to p dx plus q dy is integrable to obtain give a solution like z equal to zxy. And so in fact this procedure is to find out the common solution they have. So this method is equally applicable in any two equation where they have one solution in common. So in so based on this, in some book or in some literature they define compatibility in this manner, that f and g are compatible to each other if they have at least one solution in common, and the procedure listed here, that Jacobian is non-zero and the dz equal to p dx plus q dy is integrable, is the method to find out that common solution. So then we also discussed the procedure that in place of writing these two condition separately, can we simply look at the equation number equation f and g to say that whether they are that by f and g can we find out one's common solution, and that we have obtained in the following thing, that if bracket f g is equal to 0, that is Jacobian of f g with respect to x p plus p times Jacobian of f g with respect to z p plus Jacobian of f g with respect to y q plus q Jacobian of f g with respect to z q, if this quantity is equal to 0, then we can we are able to find out one common solution of f and g here. So here I am not saying that compatibility means what, but I am giving you both the condition that in many of books you say compatibility means every solution common, and in some book you will find out that they have at least one solution is common, but this definition may be say given in different, but they given this procedure to find out that one common solution. So I am assuming that we are using this condition that bracket of f g is equal to 0 to say that they have at least one solution in common, and the procedure that dz equal to p dx plus q dy is integrable to find out that common solution. Is it okay? So now proceed further and see what we can further achieve. So here the necessary and sufficient condition for two independent PD of the first order 1 and 2 to have an integral in common is this, that Jacobian is non-zero and the bracket is 0. And if you look at the bracket f g is equal to 0 is already involving this condition that Jacobian is non-zero, and basically this is an integrability condition, that dz equal to p dx plus q dy is integrable to this. So basically I will assume that this is nothing but an integrability condition, but in many books you will find this condition as a compatibility condition. So whatever you, if you look at compatibility means they have one solution in common, I agree that bracket f g equal to 0 is a compatibility condition, but I will assume this bracket f g is equal to 0 is a method to find out that they find out the common solution that f and g are having. So next remark is that given a PD of first order f x y z p q equal to 0 has integral in common with the equation g x y z p q equal to 0 if the function g x y z p q satisfy the following homogeneous linear PD of the first order, that is minus f p g x plus minus f q g y minus p f p minus q f q into z z plus p f z plus f x g p plus q f z plus f y into GQ is equal to 0. And in fact, this is nothing but if you have we say that here f and g have one solution in common, means the bracket fg is equal to 0, and we when you expand this, then we can arrange the like this. Here we can write it that dg is equal to 0, or we can say that gx dx plus gy dy plus gz dz plus gp dp plus gq dq equal to 0. So, when you expand this, then you can write gx into this plus gy into this plus gz into and gp equal to, and this expression you can get it from this. In fact, if you look at the coefficient of gx will be what? Coefficient of gx will be fp here, minus fp. So, that is what we have written. So, this condition that g satisfy this homogeneous linear PD of the first order, we can obtain by expanding this bracket fg is equal to 0, and we can get that g will satisfy the following homogeneous linear PD of the first order. And this is very important remark, and we will use this remark to in Charpit method to find out the complete integral of a first order nonlinear first order PD. So, let us move ahead and look at the remark 4, and this remark 4 says that if the two function f and g are independent of z, it means that they are writing only f of x y p q and g of x y p q, then the expression that bracket f g equal to 0 is simplified, and we can say that that can be written as only this thing, that parenthesis f g is equal to 0, where parenthesis f g is defined like this: parenthesis of xi eta is double xi by double p, double eta by double x minus double eta by double p, double xi by double x plus double xi by double q, double eta by double y minus double eta by double q, double xi by double I. So, it means that here when f and g both are independent of z, then we simply look at the parenthesis f g is equal to 0, where parenthesis xi eta is given by this expression. So, it is just a case of the equation the bracket f g equal to 0 when f and g are not involving any z. Now, let us consider one example based on this compatibility procedure. So, here we say that show that the equation z equal to px plus qy is compatible with any equation f of x y z p q equal to 0, that is homogeneous in x, y and z. And once we show that they are compatible to each other, we try to find out the two equations z equal to px plus qy and 2xy p square plus q square equal to z yp plus xq, and we want to find out the common solution they have. So, here I just want to note that the homogeneous equation in x y z is we say that any equation say f of x y z p q we are talking about, we say that f of x y z p q is homogeneous in terms of x, y and z if we replace x, y, z by alpha x, alpha y, alpha z, then we should get alpha alpha to power n f of x, y, z p q. And we in this case we say that your equation f is homogeneous in terms of x, y, z of the degree n, where n is the power of alpha here. So, here by this we can find out the degree, and they also have one very important relation, that is if f is homogeneous in x, y and z, then we have this relation that f of x f x plus y f of y plus z f of z is equal to n times f. Here n is the degree of the n is the power of this alpha. So, we call this as degree of the homogeneity. So, here with this information, now let us see that if f satisfy this condition, then it is compatible with z equal to px plus qy. So, now let us assume this equation f of x, y, z, p, q equal to 0, and another equation g x, y, z, p, q as px plus qy minus z, and we want to show that they are compatible to each other. So, let us look at the bracket f g and we try to show that this bracket Fg is equal to 0. Now look at the bracket Fg here, it is what, dever Fg upon dever Fg dever xp plus p times Jacobian of Fg with respect to Zp plus Jacobian of Fg with respect to Yq plus q times Jacobian of Fg with respect to Zq. Now let us simplify this further. So I can write Jacobian of Fg with respect to xp as this fx fp gx gp plus p times fz fp gz gp plus fy fq gy gq plus q times fz fq gz gq. Now here we already know that gx y z pq is equal to px plus qy minus z. Let me see whether it is correct. It is what, px plus qy minus z, px plus qy minus z. Okay. So this is the bracket Fg. Now let us simplify, since we do not have any expression for f, we simply know the properties of f, that it is homogeneous in terms of x, y and z, that is all. Nothing is given, neither the degree is given nor the exact formulation is given. So here let us use this expression for g only. So let us calculate g of x is equal to p, g of y is equal to q, g of p equal to x, g of q equal to y and g of z equal to minus 1. So using this, let us again calculate bracket of Fg. So fx fp, now in place of gx, let us gx is p here, so let me write it here, gp is x here, let me write it x here, plus p times fz fp gz is minus 1, that is given here, and gp is x, which is already calculated here, plus fy fq. Now gy is what, gy is q here, and gq is y here, let me write it here, plus q fz fq, and gz is minus 1 and gq is y. So now let us simplify this, it is what, x fx, so this is x fx minus p fp, we have simplified this, plus p times, it is what, x fz plus fp, so this is this expression, plus here we write y fy minus q fq plus q times y fz plus fq. So we have simply written down. Now we can simply say that x fx plus y fy, let us write it like x fx plus y fy plus px fz. Now here you can see that this p fp here, this will be cancelled out from this, and similarly q fq will be cancelled out by this. So what we will have is px fz plus qy fz. So this term is left and this term is left. So we are writing here, so x fx plus y fy plus px fz plus qy fz. Now if you look at, if we take out this fz common, then we have px plus qy, and we already know the value of px plus qy in terms of z, and we can write this as x fx plus y fy plus z fz. And we know that if f is homogeneous in terms of x, y and z, then this expression is nothing but n times f. Now we already have that the expression f of x, y, z, p, q, this value is coming out to be 0, so n it is 0. So we have this value is 0. So we, what we have shown here, we have calculated the bracket Fg, and we have say using the property of homogeneity, this value is coming out to be 0. So it means that any equation which is homogeneous in terms of x, y, z and px plus qy minus z are compatible to each other. Now once they are compatible to each other, then we can find out the common solution, and to find out the common solution we need to know what is the value of p and q. So here for that we have simply taken a expression for f of x y z, that is 2xy into p square plus q square equal to z y p plus xq. Now here if you look at, this is a homogeneous equation in terms of x, y and z. How we can check? You simply write this as f of x, y, z, p, q equal to, let me write it here, 2xy p square plus q square minus z y p plus xq. Now what do you simply write in place of x? Let us write it lambda x, lambda y, lambda z, p q, and if you simplify, what you will get? Here you will get a lambda square common in from first term, 2xy p square plus q square, and minus here if we write lambda z, lambda y, so again you can take out lambda square, and what you will get? Zy p plus here also from this 1 lambda and from this 1 lambda. So, lambda square you can take it out. So, x cube, right. So, when you simplify this, then it is lambda square times f of x y z p q. So, we can say that this is a homogeneous equation in terms of x y z with degree 2, right. Now, we want to show that since we have already proved that if f is homogeneous with respect to x y z and z equal to p x plus q y, then they are compatible to each other. Now, we want to show that let us take a particular form of f, that is this, and z equal to p x plus q y compatible means we can find out one common solution. So, let us try to find out one common solution here. So, here we have z equal to p x plus q y, and let me do it in a separate page. So, here we have z equal to p x plus q y, and second equation is what, 2 x y. Let me use here, it is 2 x y p square plus q square is equal to z y p plus q x. I hope I have written correctly, y p plus x q. Is that okay? Now, we already proved that it is compatible to each other. We need to find out the common solution. It means that dz equal to p dx plus q dy is integrable to each other. Now, we already know that since bracket f g is 0, so it means that this has to be integrable, because that is the condition we have already proved. So, it means that what we need to do here, we need to find out p and q from these two equations and put it here, and then use our experience to solve this equation and to get this equation as z of x y, and maybe one integration constant will also appear. So, we can get that it is a one parameter family of solution. So, now let us solve this. So, for this you simplify first equation as z minus p x upon y. So, we simply write down the value of q in terms of z, p and x and y and put it in second equation. So, let us say 2 x y p square plus q square is z minus p x whole square y square equal to z y p plus q is z minus p x upon y here. So, let me simplify this as z y square p plus z minus p x, and here we have y here. Now, here again we can write 2 x y, it is p square y square plus z minus p x whole square, and we have y square. Now, we can say y cancel and y here y cancel. So, here we can simplify further, we have 2 x, now inside it is p square y square plus z square plus p square x square minus 2z p x equal to z y square p plus z minus p x. It is given by this. Now, let us calculate the coefficient of p square here. So, p square coefficient will be what? Here it is what, and take it 2 x also common. So, here what you will get? Here we will get y square, and here we have x square. Is there any other term? No, we do not have any term. Now, let us calculate the coefficient of p here. So, let me write it here, minus p. What you will get here? 2 x is here, and here 2 z x here. So, let me write it 2 x into 2 z x. So, that is what we have obtained here, and here if we look at the coefficient here is what? Minus z y square and plus z x, yeah, and the remaining is just a constant value. So, which we can write it here as what you will get 2 x z square here. So, I can write minus 2 x z square, and here I will get my plus z square. So, here we can get a expression for quadratic equation in terms of p square, and when we can simplify for p using the theory of quadratic equation, and you can get the value of p by solving this quadratic equation, and we have equation as p equal to z by 2 x and p equal to x z by x square plus y square. I am leaving it to you. In fact, we have obtained a quadratic equation, and then we can solve for p, and you will have two values of p out of this. So, I am saying that let us do this work, and we have obtained, and we say that p equal to z by 2x is one value of p, and another value is p equal to xz upon x square plus y square. Now, once we have two values of p, then of course, you will have two values of q as well. So, let us solve for q. Let us take first value as z by 2x, then q equal to z minus px. Px is going to be z by 2 divided by y. So, it means q is going to be z by 2y. So, it means that we have now two, values of p and q. Then look at your equation dz equal to p dx plus q dy. So, let us say that dz equal to p dx plus q dy is here. Then you simply write it dz, and p is what? P is z by 2x dx, and q is what? Q is your z by 2y. So, z by 2y dy, and if you simplify this, it is what? Dz by z. In fact, you can take 2 here, then it is dx by x plus dy by y here, and here if you simplify, this is what? This is you can simplify, you can write it 2 ln z equal to ln x plus ln y plus ln c. So, we can write z square equal to c times x y. I am using c1 here. So, you can write the one solution is z square equal to c x y. So, once we have taken one value of p, you have another value for q, which we can obtain using the equation as well as this value, and we have a common solution z square equal to c x y. Now, if we use the other value, that is xz upon x square plus y square as p, then you can write you p as xz upon x square plus y square, and q is what? Q is z minus px upon y, z minus px upon y here. So, let me write it here z minus px. So, I can write it x square z upon x square plus y square divided by y, and if you simplify, z x square minus plus z y square minus x square z divided by y times x square plus y square, right. So, z x square is cancelled out here. So, we have z y is also cancelled out. So, we have z y divided there is yeah. So, here we will get z y upon x square plus y square. So, that is the value of q. So, q is z y upon x square plus y square, which we have written here, that q is z y upon x square plus y square. So, we have q, we have p. Now, let us simplify dz equal to p means p here xz upon x square plus y dx plus q dy. So, yz dy upon x square plus y square. Now, let us since we already know that it is integrable, the only thing is we have to make it in a form such that the exact integration is possible. So, here you can take out z here. So, we can write this as you can take out z here. So, we can write dz equal to yz dy upon x square plus y square plus xz dx upon x square plus y square. Then we can simply write you can take z common, and you can write dz upon z, and then you multiply by 2. So, it is 2x dx plus y dy divided by x square plus y. So, this is what? It is the derivative of z square, and if you look at this is what? Derivative of x square plus y square. So, we can simply say that you can write z square equal to some constant time c x square plus y square. So, we can say that this is another common solution they have if we use the value p as xz upon x square plus y square. So, that is what we have achieved here. So, what we have shown here, we have shown here that any equation which is homogeneous in x, y and z is compatible with z equal to px plus qy, and then we have taken a particular form of fx y z pq, that is 2xy p square plus q square equal to z yp plus q yp plus xq, and we have found out the common solution they have, and in this case they have two common solution which we have obtained by z square equal to c1 xy and z square equal to c2 times x square plus y square here. So, now based on this, now let us define a important method, that is Charpit method. So, what we try to do here, our aim is to find out the complete solution of a first order nonlinear PDE, that is f of x, y, z, p, q equal to 0. So, here we want to find out a complete solution of this equation, and how we obtain is the following, that using the concept of compatibility. So, it means that if we are able to find out another say PD, that is say g x y z p q equal to a, here a is some kind of parameter. So, we say that if the fundamental idea in this method is the introduction of second PD of order 1, that is g x y z p q equal to a, which contains an arbitrary constant a and satisfying the following condition. The following condition is that we can solve these two equations for p and q, and of course, since the equation of g will involve one parameter a, so p and q will also involve that parameter a. And then once we have the value of p and q, then dz equal to p x y z a dx plus q x y z a dy is integrable exactly. So, when we find out the solution, then we have one more parameter, and we say that our solution is given as f of x y z p x y z a b equal to 0 here, and this is given as 2 parameter family of solution, and we say that this solution as complete solution. So, here let me here the fundamental idea in Charpit method is to determine an equation g x y z p q equal to a. So, here what we say that our main problem is how to find out a differential equation, second differential equation, which is which has the following property, that by which we can find out the expression for p and q, and that the dz equal to p dx plus q dy is integrable. And here it means that the another equation we need to find out, that is g x y z p q equal to a containing an arbitrary constant a such that equation 24 and 25 are compatible to each other and can be solved to give explicit expression for p q in terms of x y z and the arbitrary constant a, that is p equal to phi x y z a and q equal to psi x y z a, and the condition of compatibility require that equation 26 is integrable, that is dz equal to p dx plus q dy is integrable. So, idea is, or the problem is, how to find out this one parameter equation of PD. So, that is the problem. So, the main problem in Charpit method is the determination of the second equation g x y z p q equal to a having the property that it is compatible with f of x y z p comma q equal to 0, and we will show that that the g and f are compatible to each other, will give you an idea how to find out this equation g, and this is quite obvious if you remember one of the remark, that g is compatible with f if g satisfies certain homogeneous partial differential equation. So, when such a given function f satisfying the above two condition has been found, it means that if we find out g such that g and f are compatible to each other and g is already having one parameter, then we can say that our solution of equation 26 is containing two arbitrary constant will be a solution of equation f x y z equal to a, and the condition 1 will be what? Condition 1 means that f and g can be solvable in terms of p and q is equivalent that Jacobian f g with respect to p q is non-zero, and that f and g are having one solution in common means dz equal to p dx plus q dy is integrable, is simply say that we can say that our bracket f g has to be 0, the value of f g has to be 0. Now, look at the bracket f g, it is f x f p g x g p plus p times determinant of f z f p g z g p and so on. So, this expression has to be equal to 0, and if we simplify, I can write this expression, that minus fp gx plus minus fq gy minus pfp minus qfq gz plus pfz plus fx gp plus qfz plus fy gq equal to 0. So, here we simplify this bracket fg equal to 0 in a way such that we write in terms of coefficient of gx, gy, gz, gp and gq. And now let us compare this equation number 28 with the following thing, that dz equal to 0. Here you have gx, y, z, p, q equal to a. So, if you find out the total derivative, then total derivative dg is coming out to be 0, and when we expand it we have the following thing, that gx dx plus gy dy plus gz dz plus gp dp plus gq dq equal to 0. So, it means that if g is given like this, then it must satisfy the equation number 28 and this equation, and if we compare these two equation, then we have the following thing, that dx upon minus fp, if you look at compare here, dx upon minus fp, dy upon minus fq, dz upon minus pfp minus qfq, dp upon pfz plus fx and dq upon this quantity, and we have a set of equations which is known as equation number 29, and we call this as Charpit subsidiary equation. So, here managing this minus sign out, and we have dx upon fp plus dy upon fq equal to dx upon fp equal to dy upon fq equal to dz upon pfp plus qfq equal to dp upon minus fx minus pfz equal to dq upon minus fy minus qfz, and these equations are known as Charpit subsidiary equation. Now, if you recall the Cauchy method of characteristics, then if you equate this value as some dt, where t is some parameter, then it is the equation which you have obtained in Cauchy method of characteristic and equation what we have obtained right now are same. The only thing is that there we have some initial condition, here we do not have any initial condition. So, that is the only difference we have now. So, it means that when we solve this equation, so then we will get an expression for g x y z p q. Here what we have seen, that here dx dy dz dp dq, basically they will characterize the surface g x y z p q g x y z equal to a, g x y z p q equal to a. So, that is our idea how to solve this equation number 30 to find out the expression g x y z p q. When we solve this, we try to do some kind of integration, and by which we have one parameter involved. So, what we try to do here, we discuss the general strategy for Charpit method. So, here transfer all terms of the given equation to left hand side and denote all expression by f. So, here whatever equation we have, you just transfer everything into one side and denote that expression by f, and write the Charpit auxiliary equation 30, and using the value of f in first step, calculate the value of fx, fy, fz, fp, fq and put in equation number 30. And then this is very important step, that select two proper fraction so that the resulting integral may come out to be the simplest relation involving at least one of p and q. So, here out of these set there are 1, 2, 3, 4, 5, you choose at least 2 so that we can get a expression, a simpler expression for p and q, right, p or q. So, once we have an expression for p and q, use the equation. The simplest relation of step 4 is solved along the given equation to determine p and q. Given equation means f of x, y, z, p, q equal to 0. So, once we have p, then of course, since they have one solution in common, then that must satisfy this given equation, that is f of x, y, z, p, q equal to 0. So, by this you find out the expression for q. So, in this way we are able to find out both p and q, and once we have values of p and q, put in dz equal to p dx plus q dy and solve for your integral, and in this way we can find out the integral, and that is the required complete integral of the equation f of x, y, z, p, q equal to 0. This is the method which we follow, and we will find the complete integral. and here we will stop, and in next lecture we will apply this strategy of Charpit method to find out complete integral. So, thank you for listening us. Thank you.